Let's talk about solving homogeneous differential equations with substitution. The differential equation dy dx equals f of xy is said to be homogeneous if f of xy can be expressed as a function of just y over x. Are these differential equations homogeneous? Dy dx equals y over x cubed plus y over x plus 2? You bet that's homogeneous. We've got a y over x cubed. We've got a y over x. We don't have any x's and y's running around. They're just all in the form of y over x. It's a function of just y over x. How about dy dx equals y over x cubed plus y over x plus 2x? Yeah, that's not homogeneous. I don't like this 2x over here. It's okay if it's y over x, but you just can't have y's and x's on their own. They have to be in the form y over x. How about this one? Wow, that one looks weird. We might need a different rule for this one. The differential equation dy dx equals f of xy is homogeneous if and only if, IFF, f of tx ty equals f of xy for all t not equal to 0. So you can show that this is equivalent to what we saw earlier, the definition. So here's what we do. We take this f of xy over here, we replace all the x's with tx, replace all the y's with ty, and we see if it stays the same. So f of xy, again, is going to be this, 4x cubed plus 4xy squared over y cubed plus 6yx squared. And then we replace all the x's with tx, replace all the y's with ty, and we end up with something like this. Multiply it out, and you get this. You got 4t cubed x cubed plus 4tx, t squared y squared, over t cubed y cubed plus 6ty times t squared x squared. And then after you distribute, you end up with this. Notice that both the top and the bottom are divisible by t cubed. So when you factor out the t cubed, you get this. T cubed times 4x cubed plus 4xy squared over t cubed times y cubed plus 6yx squared. When we cancel the t cubes, we get this. 4x cubed plus 4xy squared over y cubed plus 6yx squared. Notice that is the same as our f of xy. Okay, so in this case, the answer is homogeneous because f of tx ty turns out to be the same as f of xy. But we would only use that rule if we have some really complicated expression. We didn't need to use that rule to do this one. We could see that it was homogeneous, okay? For something like this, if it's not as obvious, we go ahead and use that other rule. How about x squared plus y squared dx minus xy dy equals 0? This looks kind of weird. It's presented in differential form. So rather than dy dx equals such and such, we have blah, blah, blah times dx plus blah, blah, blah times dy. So what I would do is rewrite it so that it's in the form that we're familiar with. Dy dx equals blah, blah, blah. So we move the xy dy to the other side. And then let's divide both sides by dx. Okay, and then we end up with this. Xy dy dx equals x squared plus y squared. Now, let's divide both sides by xy. So we get dy dx equals x squared plus y squared over xy. And we can rewrite that by breaking up the fraction. It's x squared over xy plus y squared over xy, which is x over y plus y over x. In other words, it's 1 over y over x plus y over x. It's homogeneous because it's a function of just y over x. Let's solve the homogeneous differential equation we just saw a moment ago. Dy dx equals x squared plus y squared over xy using a substitution. To solve a homogeneous differential equation, use the substitution v equals y over x. Okay, it's a function of y over x, so we let v equals y over x. That is, in other words, y equals vx, where v is the new dependent variable instead of y. Our new differential equation will turn out to be separable. Okay, so we have dy dx equals x squared plus y squared over xy. We substitute v equals y over x. Okay, remember that we could actually rewrite it like this. Okay, we had that when we rewrite it. Substitute v equals y over x. Notice that v equals y over x implies, as we saw a moment ago, that y equals vx. So let's take the derivative of both sides. Dy dx equals v plus x dv dx by the product rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. In other words, v plus x dv dx. So again, dy dx equals 1 over y over x plus y over x. Well, we know what dy dx is. We saw that just a moment ago. It's v plus x dv dx. So that's our left side Well, the right side is 1 over y over x, in other words, 1 over v, plus y over x, so just plain v. The v's cancel, and we're left with x dv dx equals 1 over v. This is a separable differential equation, so let's separate it. We're going to move the v to the other side. We'll move the x and the dx to this side, and we end up with v dv equals 1 over x dx. And then we integrate. The antiderivative of v dv, that's v squared over 2. Antiderivative 1 over x dx, that's natural log x plus c. Some books are kind of picky, and they put absolute value signs around the x. So strictly speaking, yes, you can do that. I've blown it off here, though. But you may find that your book requires this. So when we replace v with y over x, we get y over x squared over 2 equals natural log x plus c. In other words, y squared over 2x squared equals natural log x plus c. Let's multiply both sides by 2x squared, and we get y squared equals 2x squared natural log x plus c. And again, some books, some homework software may require you to put the absolute value around the x. Let's talk about a bad idea. We will see later that linear differential equations like y double prime plus 5y prime plus 6y equals f of x are said to be homogeneous if this f of x is 0. In other words, y double prime plus 5y prime plus 6y equals 0 is homogeneous. Y double prime plus 5y prime plus 6y equals sine x is not homogeneous because it's not 0. Oh my gosh, it's terribly confusing to use the same term, homogeneous differential equation, to refer to two totally different concepts. It's just an awful idea, and I apologize on behalf of the mathematical community. Sorry for putting you through this. To be honest with you, later on, when we use homogeneous differential equations, we're probably going to be referring to this concept and not the concept we're learning in this video. So, bad idea to use the same term, worst terminology in all of mathematics. Oh, but there's a worse idea, lawn darts. When I was a kid, we used to have something called lawn darts. They were these foot-long darts that had these sharp metal spikes at the bottom, and you try to throw them into the ring from a distance, which sounds okay because, well, they penetrate the ground, but they also penetrate people's skulls. And so we don't sell those in the United States or Canada anymore. But strangely enough, those are still available in Europe. So there is a worse idea than calling two completely different things homogeneous differential equations. And that worst thing is lawn darts.